This is machine learning under the hood, where I build machine learning concepts from the ground up, and then also go into the mathematical details behind whatever concept I've built up. So I'll be scrolling up and down to go through different slides, but also scrolling to the right if I ever get into more technical detail. If you want to skip this technical detail, this gives you a visual cue on which parts of the video that you want to skip. I'll also be including sections so that you can skip to whatever part of the video you want, and also another way to skip these parts of the video. So this video will be on linear regression. So linear regression is all about when you have your features and target. If you want to assume a linear relationship between your features and your target, you use linear regression. So we have the straight line equation, which I have on the left here, y equals mx plus c, and I graphed it out below. So y equals mx plus c is the equation of a straight line. C represents the y-intercept, so when x equals 0, this is the value of this function. And m is the gradient, so the rate of change or the slope of the curve. When we have our data, as mentioned in the previous video in the introduction, noise will be present in our data. This means you won't see a perfect linear relationship between two variables when you're trying to model the real world, which is much more stochastic in nature and requires more than a few features to fully describe it. So this is what happens in the real world. In the second graph, we have noise, and we see this line more or less describes the relationship between x and y, but not perfectly so. And these epsilons, which we've now introduced into the equation, here epsilon I, this represents the data or the information that we haven't captured through our features. So while there's a general trend we can see within our relationship, or a general trend we can see between target and feature, these epsilons represent pieces of information that we haven't got just through x. So for example, to take a real world example, if we're trying to predict the probability of it raining tomorrow and we use temperature to predict that, while temperature can predict the probability of it raining tomorrow, there are factors outside of temperature which dictate the probability of it raining or dictate whether it rains tomorrow. And these other pieces of information that temperature cannot capture is what is seen in these epsilons. And our goal is to try and, given the information we have, fit the best line that we possibly can. So ultimately, we're trying to figure out what theta 0 and theta 1 are. I've switched from m and c for the gradient and intercept to theta 0 and theta 1 because this is typical notation in machine learning. So now, this assumes one feature to one target. So feature is the information we're using to predict our target, which is what we want to predict. Multiple linear regression is essentially the equation for a straight line in multiple dimensions. Multiple linear regression is essentially the equation of a straight line in multiple dimensions. This is required for most real-world applications because typically you'll be using multiple features to predict your target. So our features here is x1, x2 up to xn, rather than having just one x as we have in simple linear regression. And then theta 0, theta 1 up to theta n is our y-intercept for theta 0 and the gradient with respect to each feature for theta I. So this is the same thing, but just in multiple dimensions. I've represented it here as the dots being larger when they're closer and the dots being smaller when they're further away to try and depict this third dimension that we've got here. So for example, we might be trying to predict the probability of rain tomorrow, and we might use temperature and humidity, in which case a geometric representation of this would require a 3D graph as I've depicted here. And now our epsilons, with the extra degree of freedom, with this extra dimension, now we show the error in how they can, rather than just being a straight vertical line, now these errors are sort of in all sorts of directions, which I've also tried to depict here with epsilon 1, 2, and 3. So I've got the definitions on the right here. Y is our target, as I've mentioned before. Xi is the ith feature. So for our concrete example, temperature might be x1, and then humidity might be x2. So those will be the two features in that example, but we can have as many features as we want. Theta I is the weight of the ith feature. So the bigger the number, the more of a weight it holds in our prediction. And geometrically, the more steeper gradient it'll have when we traverse in the direction of that particular feature. And theta I is what we're trying to figure out when we want to make our predictions. So we've been given xi, we have y, which is what we want to predict, and theta I is what we're trying to figure out to make these predictions. Epsilon I is then worked out after we choose theta I, because the errors depend on the relationship that you've chosen. So now I'm going to qualify the formula here that I've got. X theta plus epsilon equals y. So X here in this case is, well, capital X is the design matrix. This is a matrix that has all the information of all our observations. So it's basically a data set. So it starts off with a column of ones, and then every column after that is one column per observation or per data point. Then we have theta, which is a column vector with each entry containing our coefficients, theta 0 to theta n. Our feature values, which is again a column vector. The notation here is a bit confusing. So xi is the ith observation, and then xi1 is the first feature value of the ith observation. xi2 is the second feature value of the ith observation up to xin for n features. Earlier, I used the subscript to mean the feature, but here it's both the feature and the observation, and xi here is different from the xi before. So it's a bit confusing, and it really depends on the context. Observations, y. So we have a column vector for all our observations. And then likewise, we have a column vector f of x for our predictions. So the difference between f of x and y is that f of x is our red line here. This is our predicted relationship. Y is the genuine observed value. So here you have epsilon 1 being the difference between black, our actual data point, and where it lies on our predicted relationship, f of x. So the difference between f of x and y is just epsilon. It's just the noise that differentiates the two between prediction and true value. And so we have epsilon as a column vector, including all of our errors for all of our data points. So x times theta, that's a matrix, well, our feature matrix multiplied by our weights. And so I've just written out our definitions of x and theta here. And then I've explicitly written out every single entry rather than just generally writing the columns. So you can see every single feature value for every single observation. So this first column are all the feature values for the first observation. The second or third column, I guess, technically, is the feature values for our second observation, so on. And then we multiply it by our coefficients. And when you do that multiplication, so you do 1 times, for the top row, you do 1 times theta 0, plus x11 times theta 1, plus x21 times theta 2, so on, up to theta n xni, or xn1, sorry. And you see, you literally just get a linear regression equation from it, or a straight line equation, should I say. And when you do it for every single row, you get a system of linear equations, more or less matching up with this whole linear algebra concept of matrix multiplied by vector, of it just representing a system of linear equations. So that's why this result falls so neatly into our linear regression equation as well. Simply f of x equals x theta, where we just, as a final step, say f of x1 equals this just by definition of what we have here, of our multiple linear regression equation. We've just got no epsilon, as I mentioned before. That's the differentiating factor between f of x and y. And we've done that for each of our observations. So this f of x1 is the predicted value for our first feature, so on up to our nth feature. And this entire column vector it's stored, all of these predictions are stored in a column vector we then generally call f of x. So then, by adding epsilon, I've made it quite drawn out how I've done it here, but adding the epsilon vector on, we get f of x plus epsilon, which is just our linear straight line equation plus epsilon, and now this matches our value for y. So f of x plus epsilon equals y, as mentioned before, and so y equals x theta plus epsilon, and f of x equals x theta, as I've put here. So this is quite good because it's streamlined. We're doing every single observation, the prediction for every single observation in one go, in one multiplication. So you don't have to do it observation by observation, one computation and you're done. And in general, when you're proving things, I'll be proving certain qualities about linear regression, and it'll involve linear algebra because of this construction, which so naturally falls from the nature of linear regression and it being a system of linear equations. So now we go on to training. So training is all about, we know we want this relationship, but also we need to get the best relationship possible. It's essentially a line of best fit linear regression. You might have done that before in school. But linear regression is mathematically what is the optimal line of best fit. And the way we try and approximate this best line of best fit is through trial and error or training. So what we might do, or we do, sorry, is we start with a guess, maybe it's like that. And then we have this cost function down here. Well, I've got two different ones, SSE and MSE. SSE stands for sum of the squared errors. MSE stands for mean of the squared errors. Sum of the squared errors, or sum of squared errors, is just getting each epsilon, each error, squaring it, and then adding them together. So we're seeing how far is this red line we've just predicted away from each of our data points. But before we add up the errors, we square them. And the mean squared error is the same, but we divide by the number of points. The reason we might want the mean squared error rather than the sum of the squared errors is if we're trying to compare how good our prediction is between two different data sets with two different numbers of points. If we have one data set with 20 points and another data set with 100, and we use SSE, obviously the one with 100 data points will have a larger, will be more correlated with higher SSEs and will very likely be larger as well. But that's due to the virtue of having more errors rather than your line being less accurate. So the mean of the squared errors essentially scales it per point. And by scaling it per point, it makes it comparable between different data sets with a different number of points. But when you are just training over the same data set, it doesn't really matter which one you choose. All we want is to minimize this cost function because it's quantifying how far off our line is from predicting our data. And using SSE or MSE will give you the same line of best fit because ultimately you're just scaling it. It doesn't matter if the cost function is 100 or 1,000,000. What matters is you've minimized it. So whether if that minimum is 100 or 20, depending on which of these two you use, does not matter as long as the outcome is the same, which it will be. So we have this first prediction. Let's say sum of the squared errors here is 300. There's 30 points here, I think. So if we divide by 30, we get 10 for MSE. So we go for another iteration now, and we get this instead. And maybe this has gone down to 270. It's gone to 9. Then we do another iteration, and it looks more like this. And we get 240 for SSE and 8 for MSE. And then at some point when we're iteratively improving our cost function, by improving I mean decreasing, at some point we then go, okay, I'm happy with this, and this is your relationship now. So this iterative process, it'll sort of converge to a certain value. And the more steps and the more iterations you do, the more steps you take, the more accurate you will be. But eventually you reach a point where each iterative step is contributing less and less to improving this cost function. And it's sort of up to you to decide, after this many iterations, I'm just going to cut it off and call it a day. So we use some of the squared errors or mean squared errors, in general, the cost function of squaring these epsilons, because it's always positive. We want this to be further away from the line, means worse, rather than if we just added up how far away it is, negatives would be below the line and it would cancel out the positives. But it's also smooth. So if you just did the absolute value, rather than squaring to remove that issue of negative epsilons, you still have an issue of this discontinuous point at 0. We don't need to go into that. On top of being positive, there are a few other reasons why we might use some of the squared errors. I won't go into all of them, but a few others. One which I'll be going into in the next slide in detail is the fact that it guarantees one global minimum. What this means is there won't be two unique lines that are equally good and also the best at fitting our data. This is very useful because we know we're going straight for the answer and we're not getting derailed by some local minimum. In other training algorithms that are more complicated, this can be a real issue. But again, I'll go into this in the next slide. On top of this, sum of the squared errors actually implies that the points are normally distributed, or they're a Gaussian distribution. This is part of a broader framework, which I'll go over in my video on GLMs, where there's always a certain distribution of points that is associated with a particular cost function. So by minimizing SSE, we're inherently assuming a normal distribution among these points. So now we go into verifying the claim I just made that SSE and MSE gives one unique global minimum, or unique global minimum. So first, we call J the cost function, J of theta being our weights. We see it here. This is a mathematical formulation of the sum of the squared errors, the difference between the true observed value and our proposed value off of our approximated relationship. This is the error. It's just how far was the value from what we guessed. Squaring it first, and then once we've squared each individual error, then summing it over our n data points. I've halved it here. It's just for just to make the maths a bit neater. This constant at the beginning doesn't actually change anything. In a similar vein to how MSE and SSE are equivalent, you can multiply J of theta by any constant function, and while it might change the value of J of theta itself, or it won't change the optimal function that satisfies the minimum value, which is ultimately what we're looking for. We don't care about the exact value of J of theta, we just care about the function associated with it to minimum value. So J is convex. A brief description on convexity. I've got an example of what is and isn't convex. So if the second derivative is always positive, then your function is convex. So that means the rate of change of the rate of change. So the gradient is increasing as you increase your feature value. So the gradient here is quite negative. It's less negative here. It's flat here. It's positive here. It's bigger here. See, it's constantly increasing. And one feature of a constantly increasing gradient is it means there's exactly one point at which the gradient is 0. This means there's exactly one stationary point. The fact that it's always positive rather than always negative means that it's shaped like a downwards curve rather than like that. Negative shaped like that, which means this stationary point is always a negative, or always a minimum rather than a maximum. So since this gradient is always increasing, and it's always one minimum, and it's a minimum because it's always increasing and not always decreasing. So we have an example of what's not convex here. The gradient is low here, it increases, and then it decreases again and becomes flat here, and then it decreases more and it's quite negative here, and then it's flat again here, which means it increased. It's oscillating all over the place, and as a consequence there's lots of local minimum, most of which aren't the global minimum. The global minimum off of this curve is here, but we have a local minimum here. If our cost function reflected this curve, we could get lost in this minimum, say this is the minimum value, when in reality we could have kept going, and even though it's increasing locally, it eventually goes back down. So this is why convexity is an important feature of our cost function, or a nice one, because you don't always get convexity, but in the case of linear regression, some of the squared errors you do. So to justify this claim, first, we take the partial derivative of our cost function with respect to theta j. So theta j here is the jth weight of our line of best fit. So I've called the notation here is just a subscript theta j, but it's also equal to this here, which is the standard notation as well for partial derivative. The partial derivative means I'm taking the derivative in parallel to the axes of theta j. If you think of this as like a multi-dimensional space, an n-dimensional space, we're taking the rate of change parallel to the theta j axis. So we do explicitly for our formula here. And then next what I do is I plug in for f of x the explicit value of f of x in the case of linear regression, which we said earlier, the theta 0 plus theta 1, theta 1 minus or plus so on. But we were minusing it, so they're all negative. This is just our straight line equation. And then taking the partial derivative, well, using the chain rule, we bring the 2 out in front, multiply. This is why the half is there. It just cancels out. We then take the derivative of the inside of this bracket, multiply it out in front, which is x minus xij here, and then take one off the power of this bracket here. So when we take the derivative of the inside of this bracket, every single variable is treated constant, which means theta 0 is constant, theta 1 is constant, theta x1 is constant, only theta j is not constant. So all of these terms, other than the theta j term, which is theta ij, theta j, in this term here, this is the only one which has a theta j term, and so is the only non-constant term. And so when you take the derivative, this is the only term that doesn't completely disappear. And when you take the derivative of this with respect to theta j, just as the derivative of 6x is just 6, the derivative of xij, theta j, with respect to theta j is just xij. But because we're negative-ing, there's a negative sign as well, so it's minus theta j, xij. So now that we've taken the partial derivative with respect to theta j, we get this sum here. But notice when I talked about convexity, I took the second derivative. It's not enough to know what the derivative is. Knowing where a stationary point lies isn't enough. We need to know the rate of change of the derivative, which is the second derivative. So we need to take the second derivative, but in n dimensions, unlike in 2 dimensions where it's unambiguous what the second derivative is, since we have a choice of what variable with respect to we take our derivative, there's a whole array of second derivatives that exist. So here, we're being completely general. We generally took theta j for any j to be our first derivative, and now we're generally taking theta k to be our second derivative. So in general, once we take these two derivatives, we take the partial derivative with respect to k. I'm saying derivative so many times. By similar logic, theta k, x I k, is the only non-constant term in this bracket. And so it's the only term that doesn't disappear. And so we get minus xik. This minus xj is also a constant being multiplied by theta k, xik. So this constant stays as well, because if you expanded this out, it would be xj times yi, xj times theta 0, and so on, xj times xik times theta k. So we keep this xij term as well. And now we have two negatives, because these two surviving terms both came from this negative equation here. So these two negatives cancel out, we get a positive, and so we're left with this equation here. And I won't qualify this next equality, but this sum is equal to the j kth term of x transpose times x. J kth as in the jth row and then the kth column. So now that we have this result, ultimately the second derivative, when we have these two as our choice for the two variables with respect to that we take the derivative of, we get this element of this matrix. Now we have the Hessian, which is simply a matrix with every possible second derivative as organized as I've demonstrated here. So the jkth element of hj is taking the derivative of the jth variable, then the kth variable. Well, we've established this result, literally on the left here. By definition, as I just explained, this result is true. This is just how the Hessian is defined. And so since this equals j theta k, and this equals j theta k, theta j theta k, we conclude that these are equal as well, xtx and hj, or at least the jkth element of these two matrices. But because we did this for a general j and a general k, this holds for every single element in the matrices, the two matrices in question. So it follows that hj and xtx are the same because element-wise they're the same, so their whole must be the same as well. So now that we've established this equality, that the Hessian of our cost function is simply x transpose x, we now go into positive semi-definiteness. So the definition of semi-positive definiteness is literally just this quadratic form being positive. This is just called the quadratic form for m. The reason we care about positive semi-definiteness, I've not written it down, but if the Hessian is positive semi-definite, that then means the surface it represents is convex. Similar to how the second derivative in 2 dimensions must be positive for the curve to be convex, the generalization into n dimensions is this construction of checking whether the Hessian is positive or not. If you took it down to 1 or to 2 dimensions, you would see that it comes to just the second derivative being positive, and this is just a generalization. I won't be qualifying this statement because it would derail the point of machine learning. It's sort of out of the scope, but you can always look into it if you're curious. But subbing in the Hessian into m here, so checking if this quadratic form with the Hessian is positive, well, we can just substitute in x transpose x for h, which we do here. And now this symmetry of v transpose xv is the same as the square of the norm of xv. By definition of when you multiply something, a vector, by its transpose, you just get its norm squared. We've done that with v times x. And the square of a norm must be positive. By definition, it's just a set of squared elements. And square is always positive because these elements aren't complex. They're all real. So this is positive, and so we determine that h is positive semi-definiteness, and thus we conclude that h is positive semi-definite, and thus j theta must be convex. And since j theta must be convex, it must contain one global minimum. One requirement of this is the columns of x must not be collinear. This linear independence is equivalent to saying that our features are not correlated. Correlation can cause issues with linear regression, one of them being this global minimum. But I'll go into correlation in the next slide. So now, as I've just mentioned, we go on to correlation and interactions. So sometimes variables are correlated, and this can cause issues for linear regression. So for example, with our example of the percentage chance of it raining tomorrow, where we have temperature and humidity as two features, we see that warmer air holds more moisture. More moisture increases chance of rain. Therefore, warm air increases chance of rain. So independent of this line of logic, both temperature and humidity are predictive for the chance of rain tomorrow. Because this process is stored within both variables, temperature and humidity, that means when you use both variables to predict the percentage chance of rain tomorrow, you double count this process accounting for some of the relationship. On top of this relationship, any reason why there is a correlation between two variables will be double counted when you use them to predict chance of rain using linear regression. On top of this, or even because of this, this leads to instability within variables which are correlated, which means a small change in these variables will cause a large change in our target prediction, which we don't want. Typically, things are stable when you've got an accurate representation of the real world. I've tried to represent through the graphs you can see here. So chance of rain by temperature on the left. And then I've added literally as a third axis, just like that, in this second graph. So it's the same thing, but I've added moisture, and I've tried to depict small moisture with big dots and large moisture with small dots showing they're far away, just as I have done before. And then if you look sort of in this direction, so through the plane that is moisture and chance of rain tomorrow, you get this graph on the right here. So even though they're correlated, when you look at both, you just see this relationship of that looks like it's just a linear relationship, when in reality there's some overlapping between these two different graphs. So even though it looks like there's two separate clear trends here, in reality there's some overlapping between the trend here and the trend here. When they're correlated, if you increase temperature and the chance of rain goes up, some of that increase is actually explained by humidity as well, due to the correlation. There's also interactions. For a concrete example, the relationship you see for humidity at high temperatures might differ from the relationship you see with humidity at low temperatures. This difference means when you look at it on aggregate, it's not necessarily telling you the full story. But when you have something like, that was a triple circle, if you have something like this can then pick out any relationships between how temperature varies with how temperature affects the chance of rain tomorrow for low moisture as well as for high moisture. I haven't clearly shown any patterns here. I wasn't sure how to get it in the space, but hopefully that makes sense. So these are two things to look out for, and these are two things that can cause issues with linear regression. So now, not related to correlation, but just a slightly more technical point. Until now, we've been iteratively improving our relationship, but actually we can completely solve and find an exact solution for the line of best fit that is mathematically best in terms of the sum of square errors. In the particular case of linear regression, there's a reason I haven't mentioned it until now, and unless the data set is very small, you don't usually solve it analytically. So using the proof before we mentioned, I had this result, which you can go back in the video and see. The partial derivative with respect to theta j. Now we set this equal to 0 because we're looking for a minimum of this cost function. This is the minimum of the cost function with respect to theta j. And if we do it over all I and just write it as matrix form, so going from here to here, it's just culminating this sum to represent it just as a matrix rather than using the individual entries in the matrix. We get this equation here to represent the minimum. When we solve for theta, because theta are the weights we're trying to look for to determine our relationship, we get this formula here, x transpose x inversed times x transpose times y. Now, even though this you would think would be quite easy to use because it's just a formula you plug into, this is actually very computationally expensive to compute. So looking at this brown box here, x transpose times x is the order magnitude of n times p squared, n being the number of features, p being the number of observations, and inverting takes O of p cubed. So to do this entire computation and invert it together is O of n p squared plus p cubed, though this p cubed term predominantly dominates for large p. And p cubed, say you have 100,000 pieces of information and then you've got to cube that, 10 to the 5 cubed, 10 to the 15. That is very large, and it takes a very long time to compute as a result of that. So if you're handling big data, this analytical solution, while exact, is not realistic because of how computationally intensive it is, particularly when, as I'll go over later, one of the pros of linear regression is that it's simple and computationally cheap. you immediately lose one of the pros of this algorithm when you attempt solving it analytically if you don't have a small data set. Though for small data sets, this is a perfect way of doing it in a very simple way. But iteratively solving it, you'll get a very close approximation, and it's much faster to do. So now we go into nonlinear functions. A very common misconception with linear regression is that you need a linear relationship between your features and your target to use linear regression. I might have even used that exact phrasing earlier, but technically that's not incorrect. What you need is a linear relationship between any function between your features and your target. An example of this, if we have chance of rain tomorrow by temperature, and obviously this isn't an actual relationship, but just pretend for now, you could sort of fit a quadratic-like curve in here. So you might look at that data and go, okay, well, if I graph it against some quadratic of temperature, suddenly it turns into a straight line relationship. And at this point, we can apply linear regression, even though we initially couldn't, by using a nonlinear function to transform the initially nonlinear relationship into a linear relationship. If you can find such relationships between any of the features and even the target to make it a straight line relationship, linear regression works just as well as it usually would. So I've got the more general formula here, g of y. So rather than just our target y, some function g equals theta 0 plus theta 1 f1 x1 plus and so on, plus that theta n f of xn. So rather than x1 to xn, we have f1 of x1 to fn of xn. All these f's are all the different functions that you could potentially try and stick together and Frankenstein some linear relationship as a result. So for example here, f1 would be a times x1 minus b all squared plus c. Though, of course, you wouldn't have a family of curves as I've put here. It would be something specific like temperature squared plus 3. I just wrote a general thing because I'm just making a point. It's a quadratic relationship. But typically there would be precise numbers here rather than a, b, and c. So this makes linear regression much more versatile than you would initially think, because it seems very restrictive that you would always need a linear relationship, because that's quite a restrictive requirement to use this algorithm. So it's more powerful than you would initially expect. So a bit of a tongue twister now, homoscedasticity. This just means that variance does not change over feature values. Here on the left, we've got a graph where variance does not change with feature value. This is represented with these horizontal lines, which show that no matter how you go along the x-axis, the points more or less are contained by these two lines and more or less take up most of the space within it. Whereas on the right, we see here, the variance is decreasing as you increase the x-axis. And this is represented by this horizontal or this diagonal line, which is containing the points. The points are getting more compact together as you increase the x-axis. Thus, homoscedasticity isn't held here. So while this isn't a requirement for linear regression, it is desirable. And that's because the sum of the squared errors, as it stands when it is true, is the best cost function when looking over different data sets. When you look at the cost function for the same data distribution over different data sets, sum of the squared errors will minimize the variance of the cost function over different pieces of data. If you have a data set like this where variance changes as you change the feature values, then a slightly altered version of sum of the squared errors where you weight it accordingly to this change in variance leads to a lower overall variance and makes it a slightly better cost function. Though this is quite a nitpicky detail, it's worth noting that if your variance does change as you change your feature values, potentially some of the squared errors might not be the optimal cost function, though it's still functional. So now finally for the pros and cons of this algorithm. The first pro is it's simple and explainable. If you're in, say, a bigger company and you're showing this to people who aren't in data science, the simplicity and explainability is a huge pro. It's a lot simpler to explain to someone, when this variable goes up, our target goes up. When this variable goes down, our target goes down. This is a key feature of linear regression. One goes up, the other goes up. And at the same time, when one goes up, the other goes up at the same rate as well, which makes it even simpler and easier to explain. On top of this, even to technical people, some of these other algorithms just aren't explainable at all. And you get these black box predictions, which can be detrimental when, if the machine learning model is given something illogical and you want to figure out why the prediction that was made. With linear regression, you'll never struggle with that. But with something that's a bit more complicated and less understandable, this can be a big problem when you're trying to trust your machine learning model or try to understand why it did what it did. Another pro is it's versatile. So as I mentioned with the nonlinear functions, you can use it in a lot of different scenarios because all you need is a linear relationship with any functions of your features, which is good, especially with the simplicity. It being versatile is quite good. And finally, I also mentioned this earlier, it's computationally cheap and fast when you do it iteratively, which is good because you can get them up faster, and you can potentially even get them up cheaper if it's expensive to be training these models. The cons, most sort of contradicting what I said earlier with the versatility, but most real world interactions are more complex than a linear relationship. Even if you have that extended use case when you Frankenstein these functions together to get a linear relationship, ultimately a lot of the time a linear relationship just does not cut it, and you'll need something more sophisticated. But if it's possible, linear regression is the go-to, but oftentimes it's not possible, unfortunately. Another thing is it's sensitive to anomalies. So if I scroll back up, with this example here, we have a bit of an anomaly here. This point will impact the line. It's going to skew it into this direction. Without the anomaly, the line might be like this for line of best fit. The anomaly might skew over a bit like that. In this case, it's not too bad. But if you have a really bad anomaly, say you had a data error, and there's a point way over here, not even on my box because it's so bad, and then suddenly you're predicting something like this, because of this one point, even though it's a minority of the points, that's an issue. And again, you could get rid of anomalies, but if your data set contains hundreds and thousands of points, it could be quite annoying to try and scout out these anomalous points. And at what point is an anomaly an anomaly? How far out does it need to be for you to include or exclude it? This is a particular con for linear regression. Not every single algorithm has this trait of falling for anomalies, even if only proportional to the number of points. So in that case, it would have been 1 of 30 points. So it would only weight at 1/30th. But regardless, like I said, if it's far out enough, it will cause tangible diversion from what we would actually want or expect to be the best relationship. And then correlations and interactions, as I mentioned before, can cause instability. There are ways to get around this. Normalization, which I'll be going over in a later video. But for now, just know that this can cause issues. So typically you want to be looking for data that is not correlated if you're using linear regression. And if the data is inherently very correlated, you might want to either not use linear regression or use particular techniques to mitigate or transform the data so it's not correlated. Other things which I'll get over to in later videos as well. Finally, extrapolation beyond training input values can lead to absurd predictions. So again, going back to the data here, chance of rain tomorrow based off of let's say temperature actually. So on this leftmost graph here, say this is our relationship and we extrapolate beyond the axes, and this is the x-axis, there is a temperature at which we start predicting a negative probability, which obviously makes no sense. The reason for that is in reality, the relationship probably diminishes and goes closer and closer to zero or something like that. I don't actually know what the relationship is, because then you get snow and whatever. But generally speaking, with data, you would expect it to taper off in this manner. And linear regression does not, because it's too simple to hold the nuance of a diminishing gradient or convergence. It just assumes a straight line forever. And if your range that you have in real life data is much larger than what you trained on, or just the nature of what you trained on to begin with just didn't suit something, then you could end up with these absurd predictions. So that's a downside of linear regression as well. But yeah, that's everything on linear regression. So the next video, I'll be going over gradient descent, which is the algorithm used to find the line of best fit and in general, how we train to find the best relationship. So stay tuned for that. It guarantees one global minimum. Fuck's sake.